Welcome to Narada Academy. In this video, we are going to discuss about Sturm-Liouville boundary value problems in ordinary differential equations. So let us start with second order boundary value problems. An equation of the type y double dash plus p of x into y dash plus q of x into y equal to phi of x along with the boundary conditions alpha 1 into y of a plus beta 1 into y dash of a equal to gamma 1, alpha 2 into y of b plus beta 2 into y dash of b equal to gamma 2, where this p, q, phi, they are all continuous functions in the interval a to b. Okay, and alpha 1, alpha 2, beta 1, beta 2, gamma 1, gamma 2 are all real numbers, okay, real constants. And this alpha 1 and beta 1 should not be both equal to 0. And similarly, both this alpha 2 and beta 2 together, they cannot be 0. So, this is a second order. This is the structure of a second order boundary value problem, and this boundary value problem is said to be homogeneous when the right hand side phi of x is equal to 0 and these boundary conditions are also, right hand side of the boundary conditions are also equal to 0. Okay, now let's see one theorem for the existence of solution of the boundary value problem. Let y1 of x and y2 of x be two linearly independent solution of y double dash, that is this boundary value problem, because this is a second order problem, no, so I am taking two solutions y1 of x and y2 of x be two linearly independent solutions for this boundary value problem along with these conditions. Then non-trivial solution to the homogeneous boundary value problem, a non-trivial solution means what? Apart from 0, a non-trivial solution exists if and only if the determinant of alpha 1 y1 of a plus beta 1 y1 dash of a, alpha 1 y2 of a plus beta 1 y2 dash of a, alpha 2 y1 of b plus beta 2 y1 dash of b, and alpha 2 y2 of b plus beta 2 y2 dash of b is equal to 0. Only when this determinant is equal to 0, in that case only we will have a non-trivial solution for the homogeneous boundary value problem. Okay, this is non-homogeneous. Homogeneous means what? Right hand side is equal to 0. Okay, now consider the homogeneous boundary value problem y double dash plus p of x comma lambda y dash plus q of x comma lambda y equal to 0, along with the boundary conditions alpha 1 y of a plus beta 1 y dash of a equal to 0 and alpha 2 y of b plus beta 2 y dash of b equal to 0. The values of lambda for which the same type of boundary value problem, but here p and q depends on lambda also. Okay, the solution exists only for, that is non-trivial solution exists only for certain values of lambda, and these lambda values are called what? Eigenvalues. Okay, and the corresponding solution, so for that particular lambda you will be having one solution for this equation, no, that solution is called what? Eigenfunction. So the values of lambda for which the solution exists is called eigenvalue, and the respective solutions are called eigenfunctions, right? Now next one, Sturm-Liouville problem. See, a second order Sturm-Liouville problem is a homogeneous boundary value problem of the type p of x into y dash the whole derivative. Okay, this is second order equation only. So if you differentiate this, what will you get? P of x into y double dash plus y dash into p dash of x, right? So the general format is written like this: p of x into y dash the whole derivative plus q of x into y plus lambda into w of x y equal to 0, along with the conditions alpha 1 y of a plus beta 1 y dash of a equal to 0 and alpha 2 y of b plus beta 2 y dash of b equal to 0, where this p, p dash, q, w are all continuous on AB, and p of x, w of x are positive on the closed interval AB. This is called what? Sturm-Liouville problem. For Sturm-Liouville problem, the structure is this, and what are the conditions? P, p dash, q and this w, they are all continuous and they are positive on AB. Now, what are the properties of Sturm-Liouville problem? The eigenvalues of Sturm-Liouville problem are all real and non-negative. Okay. So, if you find the values of lambda for Sturm-Liouville problem, they should all be what? Real and non-negative. Next one, the eigenvalues can be arranged in a strictly increasing order. That is 0 less than or equal to lambda 1 less than lambda 2 etc. And as n tends to infinity, lambda n tends to infinity. So, first one is all the eigenvalues are positive. Okay, and the second one is it forms a strictly increasing sequence. Next one, for each eigenvalue Sturm-Liouville problem, there exists one and only one linearly independent eigenfunction. There exists one and only one solution, right? And then the set of eigenfunctions e1, e2 etc. of a Sturm-Liouville problem satisfies this condition. See, for lambda 1, e1 of x is the eigenfunction. For lambda 2, E2 of x is the eigenfunction, etc. So this will form a set, no? This set will satisfy this orthogonal property. Integral a to b w of x. What is this w of x? This is the coefficient of y. Okay, w of x into en of x into em of x dx is equal to 0 for n not equal to m. So this is an important property of the eigenfunctions of a Sturm-Liouville problem. Okay, now let's see some problems. The first problem, find the eigenvalues and eigenfunctions of y double dash minus 4 lambda y dash plus 4 lambda square y equal to 0 with y of 0 equal to 0, y of 1 plus y dash of 1 equal to 0. See, now as usual, how we solve the second order linear differential equation with constant coefficients, in that way only we have to do. Now the auxiliary equation is written as m square minus 4 lambda m plus 4 lambda square equal to 0. So if you solve this equation, we are getting m equal to 2 lambda 2 times, right? So real roots to equal and real roots. So the solution is given by y equal to, that is the complementary function we used to write, no? That is what I have written here. Y equal to c1 e power 2 lambda x plus c2x e power 2 lambda x. Now let us apply the boundary condition. Y of 0 equal to 0 implies c1 plus, this will be 0, no? c1 plus 0 equal to 0. So c1 equal to 0. Therefore, if you put c1 equal to 0 in the solution, what will you get? Y equal to simply c2x into e power 2x. Next boundary condition. What is the next boundary condition? Y of 1 plus y dash of 1 equal to 0. Now let us find y dash from this expression. Y dash is equal to c2 e power 2 lambda x plus c2x 2 lambda e power 2 lambda x. Okay. Now, so y of 1 plus y dash of 1 equal to 0 implies c2 e power 2 lambda plus c2 e power 2 lambda plus 2 lambda c2 e power 2 lambda equal to 0. So that implies 2c2 e power 2 lambda into 1 plus lambda equal to 0. Now this product is 0 means what? Any one of the value is equal to 0. That implies c2 is equal to 0 or 1 plus lambda equal to 0. So either c2 equal to 0 or lambda equal to minus 1. See, already we have c1 is equal to 0. If c2 is also equal to 0, that will give you only the trivial solution. Okay, so the only eigenvalue for this problem is lambda equal to minus 1. So for this problem, the only eigenvalue is what? Lambda equal to minus 1. So the particular solution for lambda equal to minus 1 is given by y equal to c2x into e power minus 2x. So this is the solution for the problem corresponding to this eigenvalue, and this is called the eigenfunction. Okay, that's all. Then next problem. Find the eigenvalues and eigenfunctions of y double dash plus lambda y dash equal to 0 with y of 0 plus y dash of 0 equal to 0 and y dash of 1 equal to 0. Write the auxiliary equation m square plus lambda m equal to 0. So m into m plus lambda equal to 0 implies m equal to 0 or minus lambda. So two real and distinct roots. So what is the complementary function? Y equal to c1 plus c2 e power minus lambda x. Now this is the solution of the given equation. Now let us apply the boundary conditions. Now y of 0 plus y dash of 0 equal to 0 implies, now let's find y dash equal to minus c2 e power lambda minus lambda x into lambda. So y of 0 plus y dash of 0 equal to 0 implies c1 plus c2 minus lambda c2 equal to 0. That implies c1 plus c2 into 1 minus lambda equal to 0. This is one equation. Next one, y dash of 1 equal to 0 implies c2 lambda e power minus x equal to 0. So either lambda equal to 0 or c2 equal to 0. See, if you put c2 equal to 0 in this equation, what will you get? Obviously c1 is also equal to 0. So c2 equal to 0 will give you only the trivial solution. So I am not interested in c2 equal to 0. Right? And if lambda equal to 0, what happens? Lambda equal to 0, then y equal to y, this is our y, no? Y will be c1 plus c2, right? But this again implies lambda, if you put say lambda equal to 0, what will you get? c1 plus c2 equal to 0. So in this case also I am getting y equal to 0 as the trivial solution. Therefore lambda equal to 0, which gives only the trivial solution. So this is again not an eigenvalue. Okay, eigenvalue means it has to give you non-trivial solution. So this problem does not have any eigenvalue. Okay. Find the eigenvalues and eigenfunctions of y double dash minus 4 lambda y dash plus 4 lambda square y equal to 0, y of 0 plus y dash of 0 equal to 0, y of 1 minus y dash of 1 equal to 0. Now first let us write the auxiliary equation m square minus 4 lambda m plus 4 lambda square equal to 0. So this gives m equal to 2 lambda, that is the repeated roots, here in repeated roots. So the solution is y equal to c1 e power 2 lambda x plus c2x e power 2 lambda x. So what is y dash? 2 lambda c1 e power 2 lambda x plus 2 lambda c2x e power 2 lambda x plus c2 e power 2 lambda x. Now y of 0 plus y dash of 0 equal to 0 implies you write the values here and simplify. I am getting the expression as c1 into 1 plus 2 lambda plus c2 equal to 0. Similarly, the next boundary condition y of 1 minus y dash of 1 equal to 0 implies c1 into 1 minus 2 lambda minus 2 lambda c2 equal to 0. See, in the beginning of the video itself, we have seen a non-trivial solution exists only when this determinant is equal to 0. Okay, that is alpha 1 y1 of a plus beta 1 y1 dash of a. This determinant is there, no, it is equal to 0. So from these two equations are obtained from the boundary conditions only, no. So the determinant, okay, this has a non-trivial solution if and only if the determinant 1 plus 2 lambda 1 minus 2 lambda minus 2 lambda equal to 0. Right, simplify this expression. I am getting lambda equal to plus or minus I by 2. See, these are only imaginary roots, no. So that it has no real eigenvalues. Okay, so for real eigenvalues it has only trivial solution, right? So no real eigenvalues for this particular problem, right? Okay, next problem, find the eigenvalues and eigenfunctions of y double dash plus lambda y equal to 0 with y of 0 equal to 0 and y of 1 equal to 0. See, write the auxiliary equation m square plus lambda equal to 0. So m square equal to minus lambda. See, I am going to discuss this in 3 different cases because here I am getting it as minus lambda, no. So I am going to discuss it in 3 different cases. Case 1, lambda equal to 0. In that case, m equal to 0. 2 real and equal roots. So the solution is y equal to c1 plus c2x. Okay, now apply the boundary conditions. Y of 0 equal to 0 and y of 1 equal to 0. That implies c1 equal to 0 and c2 equal to 0. So for lambda equal to 0, only the trivial solution is there. Next case, lambda be negative. If lambda is negative, this m square will be only positive, no. So m square will become positive. Therefore, m will be real roots only. Okay, real and conjugate roots. Plus or minus root of minus lambda. Remember, this is only a real number. Because lambda is negative, so minus lambda is positive. So square root of lambda is what? Only a real number. So the solution is y equal to c1 e power minus lambda minus root of minus lambda x, c2 e power root of minus lambda x. Now y of 0 equal to 0 implies c1 plus c2 equal to 0 and y of 1 equal to 0 implies c1 e power minus root minus lambda plus c2 e power minus root minus lambda equal to 0. As before the previous problem, this problem has a non-trivial solution only when the determinant 1 1 and e power minus root minus lambda e power root minus lambda equal to 0. Right, but if you expand this determinant, you are getting only exponential terms, but this exponential terms is never vanishing one, so this is not equal to 0. That means this problem does not have any trivial solution, does not have any non-trivial solution. Only the trivial solution exists for this problem when lambda is less than 0. So both the cases has only what? Trivial solution. Okay, now let us see what about lambda is positive. So when lambda is positive, what happens to m square? M square equal to minus lambda. So this is a negative number. So if you take square root, m equal to plus or minus I root lambda. So the solution is y equal to c1 cos root lambda x plus c2 sin root lambda x. Now the boundary condition, y of 0 equal to 0 implies the cos 0 is 1, no? So c1 equal to 0. This will be entirely 0. So c1 equal to 0. So what about y of 1 equal to 0? Y of 1 equal to 0 implies already c1 is 0, no? So no need to take this term. Only this term you take. c2 sin root lambda equal to 0. When will you get 0 for sin theta? Only for multiples of pi. That is root lambda equal to n pi. Therefore, y is equal to cn sin n pi x. Okay, right. So the eigenvalues are lambda equal to what? N square pi square, no? So n square pi square are the eigenvalues and the eigenfunctions are yn equal to cn sin n pi x. So these are the eigenvalues and eigenfunctions for the given differential equation. Now determine whether this is a Sturm Liouville problem. Xy dash the whole derivative plus x square plus 1 plus lambda e power xy equal to 0. Now y of 1 plus 2 y dash of 1 equal to 0 and y of 2 minus 3 y dash of 2 equal to 0. Obviously, yes, this is a Sturm Liouville problem. Here p of x is equal to x and q of x is equal to this one, isn't it? That is x square plus 1 and this lambda, coefficient of lambda is our w term. W of x is equal to e power x. And p of x and q of x should be, what is the interval here? That is boundaries are interval 1 comma 2, isn't it? They are continuous because they are polynomials only. No? Yes, this is a Sturm Liouville problem. Okay, that's all. Thank you.